Hello, thank you for joining us as we continue our work with vectors, and now we're going to be looking at applications of vectors. In this lesson, you're going to apply vector methods to a variety of situations and contexts, including kinematics and exam-style questions for the IB. In subsequent lessons, you'll review the vector method approaches and skills to ensure you are able to apply the vector concepts discussed in a consistent and correct manner. Now, when you're working with kinematics, it's important to distinguish items that are vector quantities, so working as vectors, such as displacement, velocity, and acceleration, those that have magnitude and direction, and distinguish those from those quantities that are scalars, such as distance, speed, and magnitude of acceleration, right? So if it's just the magnitude, no directionality, then it's a scalar. And you want to be careful about things that you can do with scalars and things that you can do with vectors. Also, remember, navigation, usually in degrees. Okay, so let's look at this particular problem. Zadar is the oldest continuously inhabited Croatian city and is situated on the Adriatic Sea. Across from Zadar lies the island of Ugljan, and that includes a small village named Preko. Let's say that we have this young lad named Luca, and every year Luca swims across the canal from Zadar. All right, so swims from Zadar to Preko. Okay, Luca's average swimming speed in the pool is 1.8 meters per second, and due to a sea current that is directly perpendicular to the route, Luca must adjust his direction to account for the 1.2 meter per second current. Determine the angle to the route that Luca should swim to travel directly to Preko. Alright, so let's say once again that here we have Zadar and Preko, and I want to go straight here. But I also know that I have a current that is acting against me. Right, I have a current that is acting against me. So let's say that the current is acting in that direction. Right, so the current's going to be in a directly perpendicular route, and we have to figure out what's going to be the angle, right? What's going to be the angle that we have to adjust so that instead Luca will swim in a slightly different direction so that he ends up getting pushed to the city that he wants to be at. Now, how fast is Luca swimming? Luca's swimming at 1.8 meters per second. How fast is the current? The current is at 1.2 meters per second. I want to figure out the angle theta, right? And so basically we can say that that part is theta as well. And this piece seems to be SOHCAHTOA, and I can say, hey, that the sine of the angle that I want to be using is going to be 1.2 divided by 1.8. So let's go ahead and make my calculation. The inverse sine of 1.2 divided by 1.8. And remember, working in degrees is the common piece for navigation. So I'll multiply by 180 and divide by pi, and we see that that's going to be approximately 41.8 degrees. Okay, and we can see down here, right, that that is the value that we got. So good. How long does it take Luca to reach Preko if the route is 4.5 kilometers? All right, well, if the route is 4.5 kilometers, I'm going 4.5 kilometers, and I'm traveling at 1.8. Well, no, that's not where I'm traveling, because this is the net effect. I want the net speed that Luca is going. And so if I look at my Pythagorean theorem here, right, let me just redraw my triangle. I need to figure out, right, that that distance there is 4.5, right? And I have, let's say, Zadar, and I have Preko, and I know my angle theta, and I know that that's 1.8 meters per second, and I know the other is 1.2 meters per second. So I'm going to have then the square root of 1.8 squared minus 1.2 squared and that unit is going to be meters per second. All right. Well, if I want to convert to meters per second from kilometers, or I want to figure out the time, because it actually is how long does it take, let me go ahead and multiply by 1,000 meters in 1 kilometer, right? And let me go ahead and multiply by, let's see, what would I need? I need my end result to be seconds, and seconds is there. So let's see what this gets me. Let's see here. Let's go ahead and multiply 4.5 times 1,000, and I'm going to divide it by the square root of 1.8 squared minus 1.2 squared. And so that gives me approximately 3,354 seconds. All right. Now, you don't really talk in seconds that much, so let's go ahead and divide that number by 60, which would mean approximately 55.90 minutes. All right, let's go ahead and subtract 55. You need to hit minus twice to get the answer minus. So let's go ahead and subtract 55 and multiply that number by 60. And so that tells me that it's about 55 minutes and 54 seconds. And we see that that is the value that we got. So this is vector approaches, but really you can see it as an old style geometry problem. Pretty straightforward, but if you don't have a good diagram, if you don't understand the context of the problem, it makes for a big difference, right? So what was the idea here? That I have Luca is trying to swim that direction, but Luca is going to get pushed by a current, and if Luca is getting pushed by a current, then the resultant is the actual directionality that Luca would be swimming, and the angle is going to be the adjustment that we want to do, and the projection or the component of the direct line from Zadar to Preco is going to be the velocity that we care about when we're talking about how long does it take. Okay, so a quick problem to discuss. Hopefully that makes sense. Stick around for additional help as you need it. Thank you for your time.